Hi ladies, this is Miss Duffy here. We're just going to go through the next part of organic chemistry. So we've talked about alkanes, we've talked about alkenes, we've talked about alkynes, and in terms of naming them, I'm hoping you got on okay with the activity I gave you the last time going through your workbook, and you corrected your answers, and that I hope went well. So now we're going to be moving on to the next set of compounds, which are benzene and what are called the aromatics. Now when you think of the word aromatic, what does it mean, do you think? Okay, so think of the word aroma. All right, so we're talking about compounds that have quite a strong smell. Now, leaving today's lesson, leaving this part of the lesson, girls, you should know the term aliphatic and aromatic, and you should know the structure and basic properties of the compound benzene. Now, alkanes, alkenes, and alkynes are all called aliphatic. They are open chain carbon molecules. Some of them have closed chains, but they are very different in structure to what we know as benzene. Okay, but aliphatic generally means, when we're talking in chemistry, means open chain carbon and hydrogen compounds. Now, aromatic compounds are ones which contain this structure here, which is what's called a benzene ring. Now, there's a number of different ways that we can draw benzene rings. We can draw it like this, okay, which obviously takes quite a while because you're ensuring that each carbon has a hydrogen attached, okay? It's got 3 double bonds here, all right? And we can draw this structure here, okay? So you're leaving out the hydrogens, but you're assuming they're there, all right? So each carbon still has 4 things attached, as always. Remember, it's tetravalent. And then finally, we've got what's called the Kekulé structure here. And the reason that we draw the circle in the center of this hexagon, girls, is because these double bonds, and we're not really sure where they are. They resonate or move around the ring. So that's what that's trying to show here, that these double bonds are moving around the ring. All right. Now, benzene was discovered by a fellow called Michael Faraday. Okay, and benzene has formula C6H6. It was originally used as a fuel. Now, due to its molecular formula, Faraday was convinced that benzene ring had many double bonds, therefore it should be very reactive, because most alkenes are reactive. We can use them for polymerization, we can use them for lots of different functions, okay? They're much more reactive than the alkanes. However, on experiment, he realised that benzene hardly reacts with anything at all. It acts more like an alkane than it does an alkene, even though it's got double bonds. So he had to do an investigation into why this was the case. So one thing that this guy here, Kekulé, noticed, girls, was when he did experiments to look at the length of the carbon-carbon chains, he realised that all the the lengths between the carbon-carbon bonds were somewhere between a single bond and a double bond. Now, single bonds are longer usually than double bonds, so you would expect this bond to be long, you'd expect this bond to be short. But he found that actually all of these guys here were the same length, and they were somewhere between a short and a long bond, somewhere between a double and a single covalent bond. So therefore, from that, he worked out that the double bonds are actually constantly moving or resonating around the ring. And so he came up with this structure here for benzene that shows that the double bond is constantly moving. So single bonds are longer. This is just repeating what I've said here. So if you want to pause the video and take this down. So single bonds are longer than double bonds. So benzene should have short and long sides, but it doesn't. Okay. And he used X-rays to show that the benzene CC bond lengths are all the same. So the word, girls, for this rotation, there's a number of different words, but resonance is probably the best one to use, okay? So or delocalization sometimes you see as well. So the double bonds are constantly moving around the ring. They're resonating or delocalized. Now, aromatic compounds, girls, they're everywhere. If you pick up your bottle of shampoo, your fake tan, anything that you use, or any food in your fridge, you'll see a benzyl something. You'll see a benzene something, all right? The benzene's in everything, okay? It itself is carcinogenic, okay? But when it's combined in compounds as part of a structure, it's quite safe to use, all right? It's everywhere. So tonight when you're in the shower, have a quick look at the back of your shampoo bottles and the back of your conditioner bottles. You'll definitely see benzyl something in there, okay? It's used as a preservative most of the time. So like I said, it's highly carcinogenic, and that caused a problem because a good few years ago, what they used to use benzene to wash your hands on leaving the lab, because it was really good at removing organic materials that you could have been using. So like it was really good for removing marker and paint and things like that. So they're actually washing their hands with something that is very carcinogenic. So that's obviously no longer done. Now, naming aromatic compounds isn't too difficult, okay? So this is methylbenzene, all right? This is ethylbenzene. This is chlorobenzene. So fairly simple. Right, so girls, we're going to move on now to what's called oil refining, all right? The next part of our organic topic. So girls, what you should know leaving today, you should know how crude oil can be separated into useful products. You should revise how the properties of the hydrocarbons depend on their chain length, and you should understand the terms octane number and knocking. Now, when you look at crude oil, we all know crude oil comes from, and we dig it from the ground, and it's come from the fossilized remains of dead organic material, okay, so dead plants, dead animals. And what it's actually composed of is it's a useless mixture of different size chains. So it's just like a load of spaghetti. You get some short chains, you get some long chains, but as a mix together, it's not a whole lot of use, okay? So to make it useful, we have to separate out the chains into different lengths, and we do this using a special process called fractional distillation. Now, you would have heard of the term distillation before. You would have done this at junior cert. Distillation is where we separate two liquids based on their boiling points. Now, this is what fractional distillation is. It looks a little bit more complicated, but what we're doing is we're pumping in crude oil, the mixture of chains, into a big, massive cylinder. Okay, and we're heating that up. And what you find is, girls, that each one of those chains has a different boiling point, and you get the long chains coming off the bottom of the column, okay, where the highest temperatures are, and you get the shortest chains coming off the top here. Okay, so here we get, for example, refinery gases. We get our methane, butane up here, okay, come off here. You get gasoline, which is petrol. It's kind of octane, okay, so that comes off in the second one. Then you get naphtha, which is usually around 9 carbons long, and that's used for making certain chemicals. Kerosene used for aircraft fuel. Then you get diesel oil, that's a longer chain again, and then you get fuel oil, and then you get residue here, which is used to make roads, okay. So these are the short chains, these are the long chains, okay? Short chains come off the low temperatures, long chains come off the high temperatures. So it's a really good way of separating out our different chains and making crude oil useful. Now, bottled gas and mains gas. So when we're in the lab, girls, what comes through our taps is actually methane, okay? But when you go to Woodies and you go and buy a bottle of gas to run, for example, a barbecue, it's actually made of propane and butane mixed together. Okay, so just be aware that propane and butane. Both of these types of fuels are odorless, so for safety reasons, sulfur is added. That's why there's a strange smell. You can always tell when the gas has been left on the lab, because we add mercapta compounds or sulfur-based compounds to ensure that you can smell when it's been left on. Now, efficiency of fuel. So not all fuels are equal, okay? Can you imagine if you put petrol into your car and before you've even paid for your petrol, it exploded and set alight itself in your engine, okay? That would be really bad. But that is the possibility of certain types of fuels. Certain types of fuels will auto-ignite or self-ignite, okay? Without any sparks being there, all right? So we have to have a value that tells us whether that's likely to happen or not, and that's called your octane number. It gives us the idea of the efficiency of the fuel, how good that fuel is. So girls, there's your definition for octane number there, sorry. So your octane number is the measure of resistance to knocking. Knocking is auto-ignition of a fuel, okay? You don't want auto-ignition of a fuel. You want the fuel to only ignite when you're ready to use the car. Otherwise, it's a big waste and it's very, very dangerous, okay? So a high octane number means it's a good fuel. A low octane number means it's a bad fuel. So here's a very, very efficient fuel here. It's called 2,2,4-trimethylpentane, also called isooctane. This structure needs to be known, and you need to know the name of this and its example of something that has a high octane number. That's a very good fuel, okay? A bad fuel, for example, will be heptane. Heptane has a octane number of 0, which means it's very likely to self-ignite or to knock. Factors which affect the octane number or the efficiency of a fuel, girls. Shorter chains have a higher octane number, okay, so shorter chains are good. A greater amount of branches, so these methyl groups here, ethyl groups, okay, anything like that. A greater amount of branches increases the octane number, and cyclic compounds have higher octane numbers as well. Things that form big circular chains are much better. Now we're going to talk about making petrol. Now, so girls, you should know what catalytic cracking is and why it's necessary, and you should know the positives and negatives of hydrogen as a fuel. Now, crude oil, like I said, girls, contains a mixture of lots of different chains. So you've got long chains and short chains. Now, unfortunately, there's lots more long chains present in crude oil than there is short chains, and short chains are the ones that are valuable, they're the ones that we want. So we have to have a way of converting our longer chain hydrocarbons into shorter chains so that, you know, we can make money from them, we can use them for fuel. So the way we do this, girls, is what's called catalytic cracking. It's the splitting of long chains into shorter chains using heat and a porcelain catalyst. An advantage of cracking is that it produces alkenes, which can then be used to make polymers. Remember, alkenes, I said, are very reactive. Now this will be an example of cracking here. So you can see we're getting a split just here at this carbon here. These two carbons split apart, and you end up with an alkene on this side and an alkane on that side, okay? So you're splitting a long chain into two shorter chains that are much more useful and much more valuable. Now the way this usually comes up in exam questions is they will generally give you the two products or one of the products and ask you what the start material is. We'll practice some examples like that in a further video. Now, so making fuels more efficient. So once we've cracked our long chain hydrocarbons, girls, we can make them more efficient again. We can increase their octane number by doing a number of things. First of all, girls, we can add branches or change the structure. So remember I said adding branches increase the octane number. So we can do this again using heat and catalysts. And this is called isomerism because you're changing the structure. You also have what's called reforming, which means you're removing hydrogen and you're creating these circular rings, again increasing the octane number. So that's done by removing hydrogen. Also, girls, you can add lead or you can add oxygen-based compounds. Now, leaded gas, girls, isn't sold anymore because it's too dangerous. It's really bad for your health and was leading to a lot of problems with people with asthmatics and people with chronic illnesses and things like that. So there's no longer leaded engine. So now they add oxygen-based compounds to increase the efficiency of fuels as well. Now, the thing to remember, girls, about fuels and when we're burning them, we always produce the same two things. Anytime you burn any hydrocarbon, you produce water and you produce carbon dioxide. We all know the dangers of carbon dioxide. It's what causes global warming. Now, that's where hydrogen comes in. We are now looking at hydrogen to see if it's the perfect fuel because when you burn hydrogen, hydrogen plus oxygen gives water. It gives a completely clear, clean waste product, no carbon dioxide at all. The problem with hydrogen is that it's very expensive to produce, so you'll do this in sixth year. So the two ways we can make hydrogen at the moment are steam reforming of natural gas, so you're still using a fossil fuel to make your hydrogen. The other way is to split water using electricity. And again, we're using electricity, which we're creating using natural gas, okay? So unfortunately at the moment, it's not really, we haven't found a good way of creating hydrogen that's clean, okay? But it is maybe, if we find a way of creating hydrogen, it will be a fuel of the future. So girls, that is all of our organic chemistry content for today. So please stop, rewatch the video, stop and pause at the key definitions. And if you have any questions, just contact me. Thanks very much, girls.